Okay. Recording has started. So good morning, everyone. Welcome back to the series on EMI test methods. I'm going to call this one a CS114 fireside chat. You can pretend that I have an image of a fireplace on the monitor behind me here. Only an image. We don't want to be thinking about any equipment here in the lab actually being on fire. So, excuse me. So we had the lecture session on CS114 on Monday. Please feel free to go back and review the video and the charts from that for any of the theoretical bits. I'm going to refer back to those charts a little bit to make some points as we go through this. But the main focus, obviously, since we're in the lab, is to actually do some stuff here in the lab and take some measurements. So with that, I'm going to call up an image from the charts here just for context. Oops, need to share my screen. Okay, so can everyone see the chart?
Yes.
Yeah, we see it.
Okay. Having trouble actually getting to. Hi, Andrea. I'm trying to get to slideshow, and it's not. All right. Well, we'll just go with this. So this is a diagram for mil standard 461G, the basic test method. You have your injection probe that's injecting the signal on the cable under test. And then you're monitoring the current into it, out of some measurement receiver, a measurement device. I'm just going to be using a scope today. And then you have your signal source, and the full setup has it going through an amplifier and then a directional coupler, and then you're monitoring your injected signal through the directional coupler. So I'm going to show you a simplified setup here, will be the main focus of today. But the broader context is that the full setup includes all this additional equipment here. But I'll show you how much more simply this can be done, at least in kind of a diagnostic manner in your development lab. And I would even say as a run for the record. And we have done it as a run for the record in the simplified way I'm going to show you. I think I'm hearing a hot mic, so if you could please mute. So we'll go back to looking at things live here. So are you back to seeing the image in the lab now?
Yes.
Okay. So I'm going to grab the camera and carry you over here to the setup. First, I'm going to show you a directional coupler. Some of these can be beasts. There are smaller ones than this, but this is one of the larger ones. Put my glasses back. Okay, I can see it's 500 watts. And from going back and looking at some of these videos, I apologize that the video quality is not very good. What I can actually read on my screen, I don't think is actually coming through on Teams or on the video. But those right there, it's 500 watts. So if you don't need as much power, if you can get by with 100 watts or 50 watts, they do become smaller. So let me turn this around. The writing, at least for me to be able to read it, is right side up this way. So here's your input. You just put your signal in through this way. This is your forward power port. So you would tap off this point to go to any measurement device, spectrum analyzer, a scope, to measure the forward power. And then here's your output to go to the destination, to your load. And then there's also a reverse power port here. So if you're not using a port, you generally want to put a termination on it. And it does tell you what the attenuation is. When you're looking at one of these ports, does that say 40 dB?
Yeah, that's what it looks like.
All right, I have my glasses for when I'm actually going to need to see things here shortly. But yeah, 40 dB. So that tells you that when you're monitoring what's coming out of this forward power port or the reverse power port, that it's 40 dB down from the actual signal. So if you're monitoring on that and controlling on it like you would be with CS114, you just need to take into account that what you're seeing here is 40 dB down from the real signal. So you'd add 40 dB to it to get to what you're actually interested in. So if you're doing a full CS114 setup from scratch or from individual components, you would need one of these to monitor your injected signal. Now, well, at least some different companies make standalone systems, more or less standalone systems. This is the one we have here at Goddard, made by Tesek, Amatec. Not that I'm trying to do a commercial or anything, just this is the unit that we have here. And it provides the injection probe that I'll be using. So we'll see that here in just a minute. It also provides you with a monitor probe. There's nothing particularly sacrosanct about using, you don't have to use a Tesek current monitor probe, but this is one they provide with this system. So why not? May as well use it. One cool thing about this probe is that it is actually an active probe. You can use it passive, like just a standard passive current probe, like most probes are. But there is a little switch here that you can turn on, and it'll turn on an amplifier, so you can get a little bit extra sensitivity out of this probe. So we're not going to use this system today. I think I'll set up a dedicated session to show how because it's kind of a different ball of wax using a specific test system and getting used to the nuances of how it works. Today I want to just illustrate the general concepts, which we'll do in a simpler system and basically just do it by hand. But one point I will make is that when you're doing power lead injection, you do need an amplifier to get to the higher levels that you need at low frequencies. As we'll talk about, the insertion loss of the injection probe is substantial at lower frequencies, and to get the desired signal at 10 kilohertz and up to about 1 megahertz, you do need an amplifier. But for common mode injection, which is what I'm going to show today, for the low level signals that we're injecting, you can do it without an amplifier. So anyway, I just wanted to show you this system here. Oh, and by the way, when you do use an amplifier, whatever power the amplifier is, I don't remember what this is offhand, but I think it might be up to about 500 watts. That's a lot of amplifier power. So if you don't need 500 watts for your actual signal injection, you don't want to rely on software control to limit the power you can inject into your equipment under test. If you inject 500 watts, you can damage stuff, and we don't really want to do that. So you usually are putting a hefty amount of attenuation on the output of an amplifier with that kind of drive capacity. So this first attenuator is 20 dB. That's pretty big lettering. I think you should be able to read that. The second one's 3 dB. So a total of 23 dB. That's a factor of 200 in power. Okay, so that's knocking the available power down by a factor of 200. So for a 500 watt amplifier, that's giving you that's hardware limiting you to about 2.5 watts that you can inject. That's a much safer level and more reasonable for most of what we do. That's as much as what I'm going to say about this system, but we'll put together a dedicated session to look at how you use this system, which is more typically how we do official tests for the record. So for today, I'm going to focus on a simpler setup. I'm going to show you a couple. Well, all right, let's move over here for a second. So here is the injection probe. Again, it's part of that Tesek system, but it's so it's a Tesek injection probe. You just saw that thing swing open really fast. I'm glad it was swinging open. You got to be careful with these things when it slams shut. And if your finger is in between there, I can neither confirm nor deny that I've ever done that. I haven't done it this morning. I've kind of learned my lesson, but you can end up with fingers that are black and blue. So you got to be careful handling this thing. And then here's the calibration fixture. So we talked about that. This will be one of the center pieces of what we'll be demonstrating, but I'll give you a sneak preview. It has a pair of N-type coaxial connectors on either end. This side has the 50 ohm, sorry about that. This side has a 50 ohm dummy load on it. The center conductor of the coaxial connector feeds through, and it's got this isolator wrapped around it, but there's a fairly hefty conductor that feeds through, and then the shield of the coaxial connector connects to the base, to the structure, of the fixture itself. So when you put the injection probe around it, it wraps around this thing. And when you apply your signal to the input connector of the probe, it ties to a coil of wire that wraps around the magnetic core. You can see the magnetic core here, and it induces a magnetic flux that is captured in that magnetic core. Excuse me, the magnetic flux couples through that loop and induces the potential in the fixture, and then we'll tie this to our scope and we'll measure it. But we'll get to that in a few minutes. I'm going to show you a couple of things here first. Go back over here to the stand. Okay. And I apologize for the poor quality of the images that get onto the video. This camera, I think, is actually pretty good. So I don't think it's necessarily a function of the camera. It's just how things translate over Teams and onto the video recording. But the way it goes. Okay. So what I've got here, at the moment, this is about as simple as it gets. And I'll take this thing off the stand once I have it set properly. Okay. I just have a signal generator that I'm going to use for everything else today. And again, the screen is very bright, but it's an RF signal generator, nothing particularly special about it, but it's a Roden Schwartz SM300. Goes from 9 kilohertz to 3 gigahertz, which is more than adequate for what we're doing today. CS114 goes from 10 kilohertz to 200 megahertz. So for starters, I've just got a 1 megahertz signal, a sine wave, at 100 dB microvolts, which is 100 millivolts RMS. And so that's what we see on the screen. And again, I apologize that I'm sure you can't read the measured values over here, so I'm just going to be reading them out. When I changed the settings, I'll even show you here. When I changed the settings on last week, oops. I absolutely love touch screens, and I also absolutely love them when there's a delayed reaction to when you touch things. That I love even more. And that's sarcasm. But anyway, if we go to invert the color scheme, at least on the team session, the things are a little more legible, but people told me they still couldn't read them. And when I went back and looked at the video recording, you still couldn't read them. So I think I'm going to stick with the normal setting because if you can't read the numbers anyway, at least I think you can see the traces better. If anybody strongly prefers the other setting, let me know. I'm happy to go back to it, but I think I'm going to go with this if there are no objections. Okay, so what I'm showing here just is the signal generator connecting directly into channel 1 of the scope. And I'm reading AC RMS, and it's reading 101 millivolts RMS. So within 1% or so of 1.5% of the expected value, right? And that's close enough for government work, as we said. So the main thing I want to show you here is, oh, let me admit, I got somebody going to come in. Okay. So the reason I'm showing you this before we even inject into the probe is the signal generator, just any RF signal generator with a 50 ohm source impedance, the level that it's telling you that this 100 dB microvolts, which equates to 100 millivolts RMS, which is what we're seeing here. When the signal generator is telling you 100 millivolts RMS or 100 dB microvolts, it's assuming you've got a 50 ohm load on there. Okay, it's got a 50 ohm source impedance, and it's telling you this is what I'm going to give you into a 50 ohm load. So down here, even though you can't read it, this tells you the settings, the quick settings for channel 1, the 100 millivolts per division, and it's on the 50 ohm input setting. So if that's too blurry for you, I guess you're just gonna have to trust me. But anyway, 50 ohms, and so it's telling us we're getting our 100 millivolts within a couple percent of RMS as expected. But now when we go to the 1 mega ohm input, so essentially an open circuit, certainly, very high impedance compared to a 50 ohm source impedance. There's our termination, 50 ohms, and we go to 1 mega ohm. Well, the signal level doubles. I didn't change anything on the generator. The generator's still putting out the same signal, but now it's putting it into a very high impedance compared to the 50 ohm source impedance. And the value that's being measured is about 194 millivolts RMS. So very close to 200 millivolts RMS, almost, essentially double. Okay. So this is very important. So why am I telling you this? There's always a reason that this is very important for understanding how the CS114 signals to make any sense out of these signals, because most of the time you are not injecting into a 50 ohm load. Even in the calibration fixture, you're injecting into 100 ohms. Because you got 100 ohm dummy or 50 ohm dummy load on one side and the 50 ohm load of your measurement device on the other, which we'll get to next. So pretty much throughout the whole process of working with CS114, you are not working directly into a 50 ohm load. So you have to really make sense out of the levels you're seeing, you have to think of it as that you have twice what I'll call the advertised signal level. If your signal generator is telling you 100 millivolts RMS, you need to double that to be your true source potential going through a 50 ohm source impedance. Okay. When you have precisely a 50 ohm load impedance, then everything is as expected. Right. The 100 millivolts RMS, and we'll go back to that. Go back to our 50 ohm input impedance of the scope. Now we're back to seeing our 100 millivolts RMS, which is what the signal generator is telling us. Okay. But when you have anything other than 50 ohms out there, which is most of what we're dealing with CS114, you have to expand your model to realize that it's double this potential going through a 50 ohm source impedance. Is everybody clear on this? This is absolutely crucial for everything that comes next. Okay. It was either crystal clear or clear as mud. So, anybody still there?
Yep. Oh yeah, we're
Okay. All right. So that's what I wanted to show you here. So now we can actually go to our injection fixture. I'm going to turn RF off. Almost thought that this was a touch screen too. But may ask you to handle the camera, if you will. All right, so I've just got to do a little reconfiguring here. So Andrea is going to handle the camera while I reconnect a few things. Oh, and I just went to the wrong side. This stays connected to the scope. So we're going to go from this cable, we're going to go to the output of the calibration fixture. I want to make sure the input, we're not running anything yet. Okay, the input, we're still going to be going into channel 1 for this next bit. That's still on the 50 ohm input setting. So that's what we want. And now we're going to put our injection probe into the calibration fixture. Probe I like to use that I have in my lab just has a little clasp on it. So it's much handier for connecting and disconnecting, but that's out on loan right now. And one of the points I want to emphasize is that, for understanding the basic physics and the basic mechanics of how to run these tests, it needs to be, as I'll say, agnostic to any specific equipment. So I sort of challenged myself to say, okay, I'm going to do the demonstration with an injection probe I'm not generally, I don't use as much, but the general concept should be the same, right? So anyway, at low frequencies, the lid doesn't necessarily matter, but when you get up to 200 megahertz, it does. So, put the lid on because it's all part of, how the fixture is supposed to give you a controlled impedance up to 200 megahertz. So clasp all this shut. And then we'll go to our more RF specific cable with end connectors on both sides. You can't quite see here, but here, go ahead and connect again. Here are the nice handy clasps so that when they're on the current probe itself, that makes it easy. But so connecting our signal generator to the input of our injection probe. Okay, so it's just a simple coil of wire wrapping around that magnetic core that induces that magnetic flux that goes through the loop here between the center conductor of the calibration fixture and the base. And so it's very simple, at least conceptually. So we'll put our lid back on. And then we bring our signal cable back to the signal generator. So now the first little demonstration was pretty much as simple as it gets, taking the RF signal generator directly into the scope. Now, all we've done is we're going through the injection probe now. So we're taking our signal from our signal generator, going into the probe, and then we're measuring what is coming out of this connector. There's 150 ohm dummy load on this side. For the powers that we're using, we probably don't necessarily need this high power load, but it's still good practice. You can see the heat sink on there. I can't read the power setting. That's probably a 50 watt terminator. Anyway, things to pay attention to with RF when you can be dissipating a fair amount of power. You don't want to put like a half watt terminator out here and then run watts through it. Then my fireside chat would become a little more literal, and so we're not going to go there. So anyway, we got a 50 ohm load here, and then another 50 ohm load coming out ultimately at your measurement device, but it's a 50 ohm input on the scope in this case. You would typically do this, or you certainly have an option to do this into a spectrum analyzer or even a network analyzer where you could do this sort of thing much more quickly. And I have done that, but I think it's instructive to do this into a scope and really slow things down so that you really see the mechanics of how all this is working. But the real key point is that your load, if you look at your load as, what is this, the induced potential in your loop here, your load is not 50 ohms, but two 50 ohm loads in series, right? It's a loop current. You might be tempted to think that the 50 ohm resistors are in parallel, and maybe at higher frequencies, they are acting more like that. But for the purposes of this test method, we need to think of them in series because you're inducing a current in the loop. All right, so you're dropping half the potential across this 50 ohm load and half across your measurement device. So what you're measuring is half the total induced EMF in your loop. that's a crucial point there too. So again, as I mentioned Monday, lots of nuances to this test method. But when you get the hang of it, it's very handy and it's a really excellent test method. So anyway, yeah, we can go ahead and put it back on there. Thank you for that. All right, so we'll go back to the scope. And this in position. And it's a little crooked. I can't be helped, but there we are. ADHD, anal compulsive, pick your poison, guilty as charged. There we go. It's a little better. It still sucks, but all right. I think we'll have to live with it. Okay. So again, slowing this down to using a scope instead of say a network analyzer, we're gonna characterize our signal through this the injection probe and through the calibration fixture. Now, I'm looking at this as kind of a simplistic calibration, but this setup is actually identical to the diagram in the mill standard for measuring the insertion loss of the setup. And I say the setup because as I mentioned on Monday, the way they define the insertion loss is it's not just the insertion loss of the probe. So they define the insertion loss in what I think is a little bit of a strange way. In fact, I think it's worth going back to that chart to review that. There we go. Can everyone see the chart?
Yeah, see.
Yep. Okay. So remember, we're not going into a 50 ohm load. So whatever the signal generator is telling you that is VO, the real signal of interest, or the thing that we have to look at for understanding how the circuit works is what I'm calling VG, the generator potential upstream of the 50 ohm load. Or I'm sorry, of the 50 ohm source impedance. So VG is going to be double VO. But the way they define insertion loss, this is the setup we have here. This is exactly what I'm doing, and this is the setup for measuring insertion loss. So I'm basically doing my pre-calibration and also measuring insertion loss of the probe at the same time. Now they define the insertion loss to be the measured, excuse me here, the VO, what the signal generator is telling you, what it thinks should go into a 50 ohm load, but that's pretend, that's not real. So I don't know why they define it this way, but there we are. But it's the advertised value on the signal generator minus the what I'm calling VCal, the calibration potential going into your measurement device. In dB, of course, both in dB microvolts. So you end up with insertion loss in dB. And so at very low frequencies, so that the physical loss of the injection probe is going to be dominated by this magnetizing inductance. So if you take an ideal transformer and throw this magnetizing inductance across the primary, that gives you a reasonably accurate model of the behavior of the system. And so at low frequencies, when this magnetizing inductance is very low or is much less than 50 ohms, it's going to dominate. Okay, so the calibration potential is going to be half of the induced EMF, because you've got half of it dropping across the dummy load on the other side of the probe, on the other side of the fixture. right? So your VCal is going to be one, this is this factor of 1/2 here, but then the induced EMF is going to be approximately your generator potential upstream of the 50 ohm source through this impedance divider, consisting of the magnetizing inductance and the 50 ohm source. And that's all this is. Okay, so the insertion loss at low frequencies is going to be dominated by the physical magnetizing inductance of the injection probe. Now at high frequencies, so when the reactance of that magnetizing inductance is much greater than 50 ohms, for very high frequencies, when it basically looks like an open circuit, you can just take it out of there, and you assume no physical probe loss. Then your calibration potential is now, you basically have your VG going through three 50 ohm resistors in series. If there's no physical loss, and this is an ideal transformer, an ideal 1-to-1 transformer anyway, just assuming a single winding for now, which this probe has, you're tapping your calibration potential off of one of these 350 ohm resistors. So it's just going to be 1/3 of VG. And so your calibration potential now so just converting this to dB, the calibration potential is going to be your VG in dB microvolts minus 9.5 dB. Factor of 3 is just 9.5 dB. We sometimes round it up to 10, but it's more accurate to say 9.5. So then, but remember that we want to put this in terms of VO. That's how the insertion loss is defined. Your VO is going to be VG minus 6 dB. So that means your VCal is VO minus 3.5 dB. So what this tells you is that even for no physical probe loss, at high frequencies, the minimum insertion loss you can get is 3.5 dB. So again, it's just how they define it. I didn't make it up. But it's just something to pay attention to when you see, 3.5 or 4, 4 to 7 dB is typical. This probe has more like 5, as we'll see, but pretend to be surprised when we get to that, because that's what we're going to measure here right now. But when you see, 3.5 dB of insertion loss, the way they've defined it, or if it's very close to 3.5 dB, then it means your probe itself has no physical or very little physical loss. So anyway, just a weird artifact of how this is defined. All right, so with that, and then here are the curves in the mill standard saying that it's recommended that you be within this range, minimum and maximum. All right, I'm gonna go back to looking at our scope. So do you see the scope now?
Yeah.
Yeah.
sir.
Okay. All right. So in keeping with the tradition that I set up last week, for doing this by hand and slowing it down to really emphasize what we're doing, I'm using my notebook. And I actually have the values that I measured the other day. I'm going to compare them to, and what I call my personal effective note taker, or PEN. Try it at home. They still work very nicely. Yeah, I know that joke never gets any better, but I'm going to keep using it. So, so we'll start at 10 kilohertz. And I'm sorry, there's one step to start with. For this simplified method, I want to just set a constant level, because this is what I talked about on Monday. You can set a constant signal generator level and sweep across the frequency range to get a constant, approximately constant short circuit current. Okay. So, and I can go back and show those charts here just to review that theory. But we're gonna, well, let me do that now, because I think that's want to make sure we understand that. And And that's actually the very next chart here in the package. So, come on. People get to see Alfred again. Okay. So Thevenin equivalent circuit analysis, I think, is a really effective tool. If you've forgotten it, it's really good to refresh your memory on it, because it's an extremely useful tool that comes into play all the time with the kind of stuff that we're doing. You can break any circuit, just define any interface that you want, and express things in terms of a Thevenin equivalent circuit. So we want to look right here at our induced EMF into our fixture, or into our cable under test, but into our calibration fixture first. So looking back from our probe, which we basically is functioning as a transformer. Looking back at this point, we can express everything to the left of that vertical line in terms of an open circuit potential and a source impedance. Right, that you can also do it as a Norton equivalent with a current source and a shunt impedance, but we're doing this as a voltage source. And so it's very straightforward conceptually. You basically open circuit this, you disconnect your load from the circuit, and you look back in this direction. What is your open circuit potential? With no load out here. Well, it's just going to be your VG through this impedance divider formed by your magnetizing inductance and the 50 ohm source, and then going through the turns ratio if it's anything other than 1. So in most cases it's going to be 1, but keeping it general, it's just your impedance divider, VG, going through the impedance divider and then divided by the turns ratio. That's your open circuit potential. Then your source impedance is formed by shorting out any voltage sources, open circuiting any current sources. We don't have any current sources here. It's just this one voltage source. So you short this to your signal reference. Notice I didn't say ground, but you're left with your magnetizing inductance, your reactance, magnetizing inductive reactance in parallel with 50 ohms. And then for impedance, it's going to be divided by the square of the turns ratio. But that's all that is. You see a mess here, but then you just conceptually realize that's just 50 ohms in parallel with the magnetizing inductance. So the beautiful thing about this is now when we look at our short circuit current, if you hang a short out here, which is what our general load is going to look like with a shielded cable connected to chassis at both ends, connected to signal reference at both ends, at least at low frequencies, that's going to look like a short circuit. And that is the theoretical maximum current we should be able to get. And that's just going to be our open circuit potential divided by the source impedance. So when we throw those expressions in here, all of those frequency dependent terms cancel. And so we're left with just the signal generator setting divided by 50 ohms times our turns ratio, which is 1 in this case. So now that's our signal generator setting, which is the advertised setting on the generator plus 6 dB. Okay. Everybody clear on this? Because this will give us this theoretically will give us a constant short circuit current capacity for a constant generator setting over the frequency range. Okay. So going to our default limit per GeVs, our high frequency calibration current is 70 dB microamps. Okay. So to get in the ballpark of what signal generator setting we want to use, let's start with this 70 dB microamps. That's 3 milliamps, basically. Okay, 69.5 dB microamps is 3 milliamps. So it's 3 milliamps and change, but I'm going to call it 3 milliamps. So this is where thinking in terms of dB is very helpful, because our signal generator is going to be dB microvolts. So 70 dB microamps of pre-calibrated current, and we're going to be measuring that into a 50 ohm load. So that's 34 dB ohms. So that would be 70 plus 34. That's 104 dB microvolts. If we had no insertion loss, then we would expect, you know, we'd want about 104 dB microvolts for our signal generator setting to give us the desired 70 dB microamps of pre-calibrated current. Now, as we said, the minimum insertion loss is going to be about 3.5 dB. There will be some physical loss. So generally speaking, about 4 dB is going to be your minimum insertion loss. So we would expect that we would need a signal generator setting on the order of about 108 dB microvolts. Now that's our VO. The actual, you know, VG is going to be 6 dB higher than that. But to get an initial idea of where we should set the signal generator, about 100 dB microvolt, 108 dB microvolts is our starting point. And as you get higher up in frequency, you'll have some losses and things like that. It's going to be a little bit harder to get the desired limit. So I'm basically gonna look at 100 megahertz to set that level. Okay. I'm going to work backwards. And so when you get down here, then you've got the loss of the probe that makes things a little more complicated. So I'm going to set the signal generator for 100 megahertz and then determine what signal generator setting I want here to get my desired pre-calibrated current. Okay? Everybody good? Now we'll actually get back to taking some more measurements, the fun stuff. Okay? So we've got everything hooked up. We did that earlier. And so I'm going to go to 100 megahertz. That's the tunnel setting. Turn RF on. Oh, and I'm going to set our level for 108 dB microvolts. That's what we said was our starting point. Okay, so 100 megahertz is a much higher frequency than where we were. So, okay, can you see the sinusoid?
Yes.
All right. We are still into 50 ohms. That's what we want. 100 millivolts per division. The AC RMS level that's being reported is 111 millivolts. Now we got to do a little bit of unit conversion here. We're looking for a pre-calibration current of 3 milliamps, but we're reading voltage across a 50 ohm load. So 3 milliamps times 50 ohms is 150 millivolts RMS. All this is in terms of RMS. Okay. So 3 milliamps RMS across 50 ohms, 150 millivolts RMS. We're reading about 111 right now, so that's a little low. Okay, so I'll bump up our signal level by another dB, so to 109. Now that's reading 125 millivolts RMS. So it's still a little low. We'll go up to 110. And that's reading 140. That's a little bit low. And so, day to day, you'll get some variations in, just the temperature sensitivity of your equipment. On Monday, 110 dB microvolts was what I used. And it was right around 149. So to compare with the, well, it's all right. I'm going to show you graphs of the data that I took on Monday with 110, but I'll go ahead and crank. I'll go give this another dB. This is 111 dB microvolts. That's actually 157. That's a little high. So, all right, let's split the difference and go to like 110.5. Okay, that's right around 150. Okay, so we'll go with that. So it's about half a dB higher than what I needed the other day. But again, temperature effects, any kind of day-to-day variability, you'll have that. I'm not too concerned about half a dB. We're not generally looking for half a dB problems with EMI. So that's the signal generator setting I'm going to use. Okay, so write down 110 dB, 0.5 dB microvolts is the signal generator setting. So now we're going to go back to 10 kilohertz and do a simplified frequency sweep. So we need the injection probe has a lot more loss at these lower frequencies, so you would expect it to have a lower signal level, as it does. Just a trigger. There's a lot of noise there too, but it's a lower signal level, so you're fighting signal to noise ratio. But okay, so at 10 kilohertz, we're looking at 17.8, well, 17.8 millivolts RMS into 50 ohms. And the other day I got 17.3. Okay. Now what I'm going to do here, I'm going to just do this as we go along. That's into 50 ohms. When we go into a 1 megohm, that'll tell you what our open circuit potential is. And it's about 35, 36 millivolts. So it's about double, right? So now you still got your 50 ohm dummy load on one end of the fixture, but the other side of it's going into essentially an open circuit, right? I mean, 99.9% of it, right? Most of it's dropping across that 1 megohm load. So you would expect it to essentially double. And at these low frequencies, your source impedance is dominated by the magnetizing inductance, so it's very low. So it will essentially double, and that's what we're seeing here. We went from about roughly 18 to roughly 36 millivolts RMS, right? So going back to 50 ohms, is what you're doing with this calibration step is establishing a maximum open circuit potential and a short circuit current. Right, you get both of those with some fixed source impedance. All right, so now going to 30 kilohertz. I'm just doing a simplistic sweep here. When you do this for real, you'd have a lot more values in between. But so I'm going to go to 30 kilohertz. Basically, on a log scale, that's roughly midway to the next decade. So 30 kilohertz. All right, our signal level goes up as we expect it would, because we're on that slope part of the insertion loss curve. All right, so now we're looking at about 57.5 millivolts RMS. And we were about 57.0 the other day on Monday, so in the same ballpark. And again, I'll go to a 1 megohm input. We're at 57 now. Go to 1 megohm. We're at about 119. So again, right around double. There's a little bit of noise there that's probably giving us a little bit of an exaggerated level, but for all intents and purposes, it's right around double. Okay. And we go to 100 kilohertz. Signal level goes up a little more. And now that's right around 101 millivolts RMS. And that's right spot on what we had on Monday. We've been within, a percent or two. And going to our 1 megohm input. It goes up to 230. So it's a little more than double now. When we're done here, I'll go back to the equivalent circuit and we'll talk about why that is. Okay. But it's a little more than double. You're getting up to the edge of the lossy part of the curve for the probe itself. Okay. So now we go to 300 kilohertz. And I'll show you a graph of this for the data that I took the other day, here when we're done. All right, we're still under 50 ohms at 3. Oh, I don't miss it. Okay, at 100 kilohertz, we're at 125 millivolts RMS. It was 124 the other day. So far, so good. We go to 1 meg ohm. And it's about 303. So again, a little more than a factor of 2. We're actually approaching a factor of 3, which at these high frequencies is closer to what I would expect. So I'll show you the schematic here again when we're done, but it gets back to, you have a 50 ohm source impedance now, because on this at the higher frequencies, certainly above about 1 megahertz is where you're on the flat part of the insertion loss curve, where the physical loss of the probe is not very significant. And then you're looking at the 50 ohm source impedance, from your signal source, from your signal generator, going into the full 100 ohm load of the fixture. So, and you're only tapping off of one of those 50 ohm loads. So at these higher frequencies, theoretically, you would expect the open circuit potential to be approaching a factor of 3, what you're seeing into that 50 ohm load. At the lower frequencies, the source impedance is much lower. So you're getting closer to the factor of 2. Okay. Anyway, I'm just going to stick with the 50 ohm load here to finish this out, and then we'll talk about what we're seeing. All right, so that was 300 kilohertz. We'll go to 1 megahertz. Now we're getting to the flat part of the curve, so it's not as dramatic when you change frequencies now. So at 1 megahertz, now we're at 145 millivolts RMS. So not quite our 150. So we're not quite to the flat part of the curve yet, but we're very close, because 150 millivolts was our target to correspond to a 3 milliamp calibration current. Okay. So yeah, 145 now, and I was reading about 143.5 the other day. Now I'll go to 3 megahertz. And now we're at 160 millivolts RMS, 158.5 on Monday. And when you look at this on a dB graph, you won't even be able to tell the difference. So 10 megahertz. That's 174 millivolts RMS, 172.3 on Monday. And 100 megahertz. We'll just call that 150, like 146. So that was our target. Actually, now we're closer to the 150. Right. Okay. So right. Anyway, so 150, 149 and change was 146.4 on Monday. And the last one will be 200 megahertz. This is the high end of the frequency range. 200 megahertz. Okay. Now it starts to decrease a little bit. You're getting some additional losses and parasitics. But now we're about at 110 millivolts RMS, 106.4 the other day. Okay. So now I'm going to show you a graph of the data that I took the other day, which was very close to what we just saw. Oh, that's just in Excel. I didn't put it in any charts or anything. But so can you see this? Can you see the graph?
Yes.
Okay. So this is within 1% or 2 of what we just saw. So it's essentially the same, and I converted it into dB microvolts. right? It's a nice thing about Excel. I can load the numbers up directly in, in what I measured and then convert into dB microvolts. So the dark blue curve are the levels read into 50 ohms. And then the orange curve is going into 1 megohm. Okay, so you can see that at 10 kilohertz we're fairly low, and then the levels come up and then asymptote more or less above about a megahertz. It's pretty typical for these injection probes to level off right around a megahertz, and that's where the knee in the curve of the limit line is, which I don't believe I've ever seen it written down anywhere, but I'm pretty sure that's by design. It would just tend to make sense that you can get those limit curves pretty closely by injecting a constant level through the injection probe, and the probe's insertion loss will give you something very close to that curve, which is what we're taking advantage of here. Okay, so at the low frequencies, you're getting the level going into 1 megohm, into effectively a high impedance, is about 6 dB higher than what you get into 50 ohms. But once you get up to about a megahertz and above, now the level you get into a high impedance is about 10 dB higher, or about a factor of 3. And if we go back to our equivalent circuit, yeah, here we go. At low frequencies, your source impedance is dominated by the magnetizing inductance. So at low frequencies, that's a very low source impedance. So whatever you're injecting, here your EMF is divided between the 50 ohm coaxial load and just the dummy load on one end of the fixture, and then what you're tapping off here, your VCal going into your measurement device. So when this is, you get one reading when this is set for 50 ohms, and then you go into 1 megohm, then the level essentially doubles when this source impedance is low. At the higher frequencies, above that knee in the curve, where the inductance is not really a significant part of the circuit, now you're looking at this total 50 ohm source impedance. So now you go from your calibration potential is now this VG divided amongst these three 50 ohm resistors. So you're getting 1/3 of VG. And in fact, that's on another chart. But anyway, but then when you go to an open circuit here, now you're getting all of the VMF. Your VMF now is essentially going to equal VG. You've got no load here anymore, right? If this is a very high impedance, there's no significant current flowing in this loop, so there's no appreciable voltage drop across your dummy load anymore. All of it's dropping across VCal. So VCal is essentially going to equal VMF, which is essentially going to equal VG. So in that case, your VCal is going to be about 3 times into an open circuit, into 1 megohm is going to be about 3 times what you will see into 50 ohms. Okay, so again, it's another subtlety of this test method that you have to take into account, that the real source potential is this VG that's going to be double what the signal generator is telling you through a 50 ohm source impedance. And then the effective source impedance of the circuit is going to be frequency dependent. It's going to be dominated by this magnetizing inductance at low frequencies, but then at high frequencies, it's going to look like the full 50 ohm source impedance. So that's why this curve looks the way it does, that at low frequencies, your open circuit potential is going to be about 6 dB higher than what you get into 50 ohms. And then at higher frequencies, it's going to be about 10 dB higher. You're going to kind of go through this transition, and it's going to be about 10 dB or a factor of 3 higher. Then you get, parasitics and stuff at higher frequencies. And when you're going into that 1 megohm load of the scope at 100 megahertz, it's going to be a less reliable reading. So that's just some of what's happening here. But I thought that was worth pointing out, because that open circuit potential, what your drive potential is into an open circuit, is one of the limits that you're trying to establish. with this pre-calibration step. Now, another thing I did here, I just took that same graph of the signal going into 50 ohms, and the insertion loss, the way it's defined, is just your signal generator setting, VO, V out, right, minus the measured level into your 50 ohm load, right? So this is your insertion loss, just this difference, okay? If you really wanted to do this properly, you would take your signal generator into that 50 ohm load and verify that that's what you're getting across the board. I would expect that there's some parasitics that are probably dropping the actual level into the scope, maybe at these higher frequencies. That's probably contributing to this. But just taking it at face value, where our signal generator setting is 110 dB microvolts across the board, pay no attention to this curve here. You're going to be surprised because I'm going to show you that one. That's our short circuit current, which is what we're building up to. But when you subtract the measured level into your 50 ohm load from the signal generator setting of 110 dB microvolts in this case, you get the insertion loss of the whole injection system. It's not just the physical loss of the probe. It's the injection circuit as it's defined. So you have 25 dB of loss at insertion loss at 10 kilohertz. And then the knee in the curve looks like it's a little closer to 10 megahertz actually, but your minimum insertion loss is about 5 dB. So this is a little more of a lossy probe than other ones I've used, but that's okay. I mean, so we've characterized it, and we know that we have to take that into account when we use this probe. So there's our insertion loss, and again, I think this level is probably an artifact of just some additional losses and parasitics getting up to 200 megahertz. So we've done our pre-calibration and we've measured our insertion loss of the probe, and basically at the same time. Now this is a very crude measurement with just at each decade, and then at 3 times the decade level, right? So 10 kilohertz, 30 kilohertz, and so on. Right? 3 is roughly halfway between. And to do this more comprehensively, you use a network analyzer, and I've done that, but I just thought it was informative to go into a scope, among other things, to be able to just select the 1 megohm input. On a network analyzer, you're stuck with 50 ohms, which is fine. If that's what you're interested in, is just getting a quick measurement of insertion loss and do your quick calibration, most of the time that's fine. But I wanted to just go into the scope to be able to show a few additional things here. So this establishes your open circuit potential, at least up to 10 megahertz or so. I don't necessarily trust these levels as much up here, but you in the worst case, you basically could say that this line more or less extends here, that you're going to be about 10 dB higher than these injected levels. So now we want to see, what do we get into a short circuit? That's kind of ultimately what we're interested in. Most of the cables that we're going to inject into are going to be shielded cables, terminated to chassis at both ends. So it's going to look like, at least resistively, at low frequencies, it's going to look like a short circuit. So let's have a look at how that behaves. So I'm going to stop sharing. We should be looking at the scope again. Everybody with me so far?
Yes.
Grabbing the camera. All right, I'm going to turn RF off. These levels are not. There's nothing unsafe about these levels, but it's just a good practice to turn your signal off when you're mucking with them. So, all right, I'm going to take the injection probe out of the fixture now, and here's where I'd love my clasp on my other probe, but it's okay. It does have a little slotted, a slot for a slotted screwdriver here. So, it's still reasonably quick to get this thing off. we take care not to pinch our fingers as we're moving this. And so for the purposes of what we're doing here, we're basically done with this fixture, so I'm gonna move it out of the way. Okay, so we just gonna keep this right here. Now, after you've done your calibration, you generally you want to keep everything in your drive circuit exactly as it was. So same cable, because even though up to 200 megahertz, you shouldn't have a whole lot of loss at 200 megahertz. Cable loss tends to be a lot more prominent getting up to a gigahertz. But at 200 megahertz, you're gonna have some. So it's just good practice to keep everything exactly the same. In fact, it's preferable to not even make any disconnections if you can, right? Because when you disconnect an RF cable and reconnect it, you might get just a slight change in behavior, right? Depends on yeah. Got an RF guy right here, and so yeah. Now with RF, when you're dealing with like tenths or hundreds of a dB, that's much more crucial. But still, it's a good practice. Leave it connected if you can. Not the end of the world if you have to disconnect it, but but definitely use the same cable, use all the same drive circuitry. That's part of what you calibrated. So now I've got a very, 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 very high tech piece of equipment. This is what I call my shielded cable simulator. I guess that would be an SCS, right? So this is our shielded cable simulator. So basically it's just something to look like a short circuit. So we'll put a short circuit here. All right, there's our short. And now I want to measure the current. So you would normally, like, you're going into like say that that pull up system over there, you would be using the current probe. Go ahead and grab that. It's show and tell. Using a full up system, which we'll demonstrate another time, you would use, whatever current probe. Well, this is the current probe that comes with this system, but you can use basically any current probe, but you would have to make sure you've programmed into the system what the transfer impedance of this probe is as a function of frequency. Because it's only going to measure the voltage that is coming out of the output connector and through the cable. So that's all part of what you have to upload into the system to make sure that you're translating that measured voltage into the current that caused it. So I could have done that, but for the purposes of this demonstration, the fact that my cable simulator is just a single wire and I can fit a scope probe, current probe around it, that's what I'm going to do. Because then we can just see the current readily without having to do that translation. All right, so I'm just putting the current probe on here. And so we're just going to play back those levels into a short circuit and see what we get. Okay. Now you have the arrow on the current probe for what this is just a loop, so it doesn't matter. But when we inject into the unit under test, you want to pay attention to that, to the direction. When you're making time domain measurements, the direction of the positive current is important. But for right now, we're just looking at magnitude, it doesn't matter. Okay, so our high-tech, expensive shielded cable simulator, SCS, is in place. We've got our current probe around it. And playing back the levels is very straightforward now, because it's just our signal generator setting of the 110.5 dB microvolts, and away we go. So we're not looking at channel 1 anymore. Looking at channel 2, and these Hall effect current probes. It's sometimes very hard to completely get rid of a DC offset. You see there is a little bit there. So, but that's why, again, I apologize, can't see the measurement values here, but if your scope can actually be set to measure AC RMS, that's what you want to use, because that'll take out the DC component. What you want to measure is the AC RMS component. Not all scopes, at least older scopes will do that, but if you have a newer scope that has that capability, that's what you want to use. All right, so now let me go back to 10 kilohertz. So the setting is still 110 dB microvolts. And I'm going to go back to my notebook and personal effective note taker and turn on the RF. Oh, I'm sorry, that's 10 megahertz. Units matter. All right, that's 10 kilohertz. Yeah, find our signal. Oh, and that's a lot of noise on it, but there we go. I'm gonna need to put a DC offset on this. This scope's a little different from the one that I'm used to, so it's always interesting getting used to the nuances of different scopes, but there we are. All right, so there's a lot of noise riding on that, but we can still get reasonable rating. I gotta change the trigger. We're actually triggering on this signal and not channel 1. Okay, it's close enough for government work. All right. So so this is our short circuit current at 10 kilohertz. Our pre-calibrated level was 3 milliamps. Okay, so we would expect normally when you're doing this as part of a control loop, you would level at 6 dB higher than that pre-calibrated level in the plateau, so 6 milliamps. For what we're doing here, just playing back the levels and seeing into a short circuit and seeing what we get, we would expect them to be about three times that, right? Because of the 50 ohm source impedance into the 100 ohm fixture. So what we're actually measuring is about 11.8 milliamps. That's right in line with what I measured on Monday, 11.5. So it's a little high, but then remember that I did adjust the level intentionally to get the desired reading at 100 megahertz. So at these low levels, we may run a little bit high. So if that really concerns you, you could adjust the level to go down a dB or so, what have you. But then you might have an undertest up at the higher frequencies. I always tend to err on the side of a slight overtest. You know, and between 9 milliamps and 12 milliamps, you're not going to break anything, right? I'd rather have a slight overtest at some frequencies than a slight undertest at others. That's just my preference. But anyway, that's our short circuit current at 10 kilohertz. That's 11.8 milliamps RMS. So remember that the voltage curve increased as a function of frequency until it leveled off a little bit above a megahertz. I saw a question pop up. But by the way, I just happened to look up. I don't, when I'm in the midst of this, I'm not generally looking at the chat. So if you have a question, please speak up. But there was a question, what's the resolution bandwidth? That's an interesting question, and I'll actually address that. That's a good question. This is the full bandwidth of 1 gigahertz. And I generally default to using the full resolution bandwidth because when you do bandwidth limit the signal, I mean, it looks better, but it's giving you it's artificial, right? It can fake you out. So, okay, we go to a 20 megahertz bandwidth. The signal looks a lot better, and we actually get a better read on the actual injected signal of concern. And it's reduced the measured value to like 11.5. It was 11.8. So it doesn't change it by that much, but it's a much better looking signal. But that said, we're trying to go up to 200 megahertz. So I don't really want to limit my bandwidth I don't want to limit my bandwidth to 20 megahertz. That's that's an interesting point. I'll come back to when we get through these measurements here, because when I use the standard current probe that I would be inclined to use, table long enough. This is the current probe I like to use for time domain measurements because it's got a flat response, but only above about 100 kilohertz. So down here at this frequency range, it's still going to give you a compromised reading. But when I did look at it with this probe the other day, the signal level was much cleaner. So I think a lot of it just has to do with that it's a fairly noisy probe, and we're actually not terribly close to the noise floor, but we're just getting a lot of excess noise through this current probe. So, but that's a good question, but I'm just going to keep it on the 1 megahertz because we're going up to 200 megahertz. Even the 250 megahertz bandwidth limit is that I'd rather not use. So anyway, going up to 30 kilohertz, our reading is about 11.8, 11.9 milliamps RMS. So at 30 kilohertz, right, our frequency changed, but the signal level, okay, it's gone up, but to like 14.3, which is right in line with what I had on Monday. I mean, it should be. This should all be very repeatable. And going up to 100 kilohertz. Again, 14.3. So we're still very much on that linearly increasing part of the insertion loss characteristic of the probe, but we're getting essentially a constant current into a short circuit as we expect. And 300 kilohertz. And you just see visually the level is not changing that much. And at 14.0, and on Monday I was at 13.5, and that's the noise level is probably giving us some variability there. So now we go to 1 megahertz. 14.5, 13.9 the other day. 3 megahertz, 13.4, 12.9 on Monday. 10 megahertz, only a few more data points. But 10 megahertz, 12.4. And 11.8 the other day. What I'm guessing is, since I cranked the level up by a half a dB, I think on Monday I had let things settle for a bit longer before I started taking measurements. I think the thermal, it thermally stabilized more. I think that's part of what we're seeing here. So if I took this back to the 110 dB microvolts that I was using Monday, I bet the readings would be much closer. But they're still close enough for purposes of what I'm doing here. So that was 10 megahertz. So let's go to 30 megahertz. All right, now we're starting to get the level is decreasing. Because now the inductance of our loop is starting to be evident. But at 30 megahertz, we're reading about 9.1. 8.4 the other day. And 10 megahertz, or I'm sorry, 100 megahertz. All right, now it's basically in the noise floor. And at this point, I'm going to show you the graph of the readings that I took on Monday. Then it, you know, you can see everything kind of at a glance. So, all right, can you see the Excel file again?
Yes.
All right. So this is a graph of basically the same set of readings I took on Monday, converted to dB microamps. And you can see within a dB or two, it's a very flat short circuit current up to about 10 megahertz, and then it starts to fall off because the inductance of that loop is going to start to come into play. And you know, not much I can do about that. That's about as small a loop as I can get through that probe. So what I go with is the high frequency performance is what I know from doing the pre-calibration into the impedance controlled calibration fixture. And then this is a verification step that I can perform to tell me I'm getting that constant short circuit current that I want at the low frequency end. So these two curves together kind of give you the fuller picture. Right. This curve follows the contour of the limit line, which is defined as a pre-calibrated value into that 100 ohm calibration fixture. And the this verification step tells you that you're getting a desired flat short circuit current, at least up to about 10 megahertz. This is actually pretty good. And let me pull up the charts. In the later part of the charts here, I have basically the same thing I did with my injection probe of choice, which is on loan that somebody's using for a test of real of at least development hardware. But it's the same basic idea here, where you get your insertion loss measurement, and then and do the verification into a loop of wire. You have to take into account, again, this is the very same probe. Actually, I'll show you this one in a minute, this F33-2 probe. It's got a nice flat transfer impedance above a couple hundred kilohertz. But below, since we're going down to 10 kilohertz, you need to take into account this transfer impedance, which that's if you're not in an automated system where you can just upload this, you know, if you're just doing this by hand, that's a bit more tedious. So I'm not doing that right now, but I did do that for these measurements. And actually, okay, this is pretty consistent. You get flat current up to about 10 megahertz, and then it starts to fall off. But so that again just, you know, underscores that you should get pretty consistent results without depending on a particular piece of equipment. I should be able to substitute any other RF signal generator, any other injection probe specifically made to support CS114, you know, and so forth. But and again, it's, you know, this has a black casing, so that's clearly a different shielded cable simulator, but it's the same basic idea. But I did say that I would hook up this other current probe. Oh, let me stop sharing. Okay, you should be seeing the view of the scope again. So I'm just going to take this other current probe, this F33-2. I think it's the same probe that was in that picture. It's at least the same model. I've got 2 or 3 of these things. So I'm going to put this current probe around that loop as well. And had this in a little bit less of a mess yesterday and set up, but here, if your lab setup is not messy, it means you're not doing anything. At least that's my code of ethics. Okay, so let's we'll go back to 10 kilohertz. Okay, so we got a good beefy signal there at 10 kilohertz. And I'm going to turn on channel 4, where I have the new current probe or the Fisher current probe. Oh, sorry, that's not the days. Actually still a little bit noisy, but there we are. Must have been looking at a different scale. I thought it was a little bit less noisy when I was looking at it through this, but there we are. So we are looking at a fairly low level signal, so that there and there may just be a fair amount of noise on it. Now at 10 kilohertz, you're on the slope part of the transfer impedance curve of the Fisher probe. So when we go up to 10 megahertz, then we know we're even at 1 megahertz, we're solidly on the flat part of the curve. And the meant to point out when we were actually looking at it, the transfer impedance of this Fisher probe above that knee at a couple hundred kilohertz is right around 1 ohm or 0 dB ohm. So it means what you read in volts is the current in amps. Okay, so that's also very handy. All right, we were at 10 kilohertz. We were getting we're on the low part of the transfer impedance curve, so it was giving us a low voltage. So okay, up here at 1 megahertz, we're getting a beefier signal. So we're further away from the noise floor. Okay, so now again, you can't read the numbers, but measurement 2 is for the blue trace, which is the Hall effect probe we have been looking at. That's 14 milliamps RMS. Measurement 3 is the green trace for the Fisher current probe, and it's 13.7 millivolts RMS, which is 13 milliamps RMS. So they're getting close to the same value, and the noise that's riding on top of the blue trace is probably giving a slightly higher value. Okay. So that's this for this simplistic setup. This is the verification step. Now we will do a quick demonstration of injecting into our EUT, and then that will wrap things up. So, does anybody have any questions here before I move things over to the EUT? Okay, turn the RF signal off. Do a little reconfiguring here. Not using this. Let's put this to the side. And that's either. So we're going to put our injection probe around the primary power cable to our EUT. I'm only going to show common mode today. We'll reconvene to show power lead injection, and that's where we need amplifier power, and we're going to need that automated system for that, which also means I need the EMI lab guys to help me with that, because I don't know how to run the software that operates that system. So I'll need their help to demonstrate that. Okay, so we're just going to show common mode. So I'm going to connect the probe around both wires. So it's the composite bundle for common mode. For power lead, it's just positive and negative leads. For if it's a shielded volt cable, you just clamp it around the entire cable. So, and you see it just clamps on. You don't have to disconnect anything. Okay, so and our input to the probe is connected to the signal generator still. The main thing we're going to be monitoring is our injected current. And again, this will be kind of a crude version of it with this simplistic setup. I do have an arrow marking the direction of positive current flow for whatever it's worth. Again, it's not terribly important for this, but if it's there, why not? I will have that going toward the EUT. Now, strictly speaking, you could just inject your pre-calibrated levels, or in this case, your constant signal generator levels swept across the frequency range. But it's good to have some way of monitoring that you are actually injecting a signal, right? So, what the current is telling you is less important than you actually have some indication that you're injecting something. In fact, at low frequencies with no shield, we generally test, our test cables for power are generally unshielded for EMI. So with no shield at low frequencies, it should be a high impedance. So we shouldn't, and we won't get much current at low frequencies. But as frequency goes up, other paths, capacitive paths and stuff come into play, and you will get some more current. But the behavior of the current is going to be frequency dependent. So, I always emphasize, do hook up a current probe and make sure that you're actually seeing something injected, but you're going more with your pre-calibrated levels. The pre-calibration step is absolutely crucial. Do not bypass that. That's how you know what you're injecting. And then when you hook up a current probe, or if you're able to monitor voltage, which we are going to do here, then you can monitor, at least get some indication that you are indeed injecting something. So as I say, I have this differential voltage probe that we had been using for CS114 and such. So it's still hooked up to our primary power input. You may not always have access to that, but I'm going to go ahead and hook this up just because it gives us something else to look at. Now we are injecting common mode. So before, I had this hooked up in a differential manner across the positive and negative terminals, power input. But because we're injecting common mode, I'm a little more interested in what is being injected on this point with respect to the ground plane. So we have this braid that just happens to be handily located right here. I didn't do this on purpose, but this braid is hooked up right, to the ground plane right here by our EUT. So I'm hooking up the return of the scope the scope probe to the ground braid. Okay, then I'm also monitoring the secondary voltage, the 15-volt output of our power converter with respect to the braid. Because when I looked just across the output differentially, it has decent common mode rejection, and you didn't really see much. I'm more interested in what is the common mode that's getting through. So we're going to look at both of those. So I'm going to plug our primary into channel 1 and secondary. That's this probe. Take that into channel 3. Channel 2 is the current probe, the Hall effect probe. We're not actually going to use that, so I'm going to turn that trace off. Channel 1 error. Okay. Tell me I can't read what's on channel 1. Okay, it took it that time. So, we're going to have to find our signals again. So that's going to be riding on top of 30 volts. So, all right. All right. So second and third set of eyes. We got our signal generator going into our injection probe. Signal generator through this cable here. It's the same cable we've been using connected to our injection probe. Clamped around the power feed, the power cable to our EUT. Our monitor probe also hooked up in common mode manner going to channel 4 or scope, the green trace. Primary power input with respect to the ground plane hooked up to channel 1 of our scope. So that's this one. Channel 1, and then the secondary also reference to the ground plane going into channel 4. Okay, so far so good. And I'm gonna go ahead and turn the EUT on. We don't have to worry about the, like with CS114, we said our drive circuitry had to be turned on before we turn on the EUT. It's still a good idea to do that here, but it's less crucial. But it is true, our signal generator is still on, just RF is off. So, all right, I'm gonna turn on the EUT. Now, yeah, I wasn't sure I was gonna show that, but now that it's there. All right, first we gotta find our signals of interest. Triggering on a signal that we're not looking at, so that doesn't help. All right, we need an offset on channel 1. There's a lot of noise, but we know that it's a noisy power converter. Okay, so that's basically our channel 1 is our power input, and we got the switching transients that we know are going to be there. Channel 4, that's clipping. Down a little bit. Okay. All right, now channel 3 is the 15 volt output. And because it's floating, right, there's no deliberate connection to the ground plane. When the output is switching, from 15 volts, or both outputs are, switching plus minus 15 volts, or just, I guess it's when the switching action inside the converter is slamming between 0 and 28 volts. It's basically throwing the reference of the output around. That's 5 volts per division. So what you're seeing on the secondary is the output being thrown around with respect to the ground plane. So what I'm going to do here, make sure you can take the camera off. So this is definitely not something I would recommend you do with an actual system, but for the purposes of this demonstration, I'm going to take the output reference here, the black wire. I'm not, trying to defuse a bomb, so it's less crucial. Would you always cut the green one? I don't know. But going from the black wire to the braid. So now I'm tying the output reference to chassis, which is generally what we do. Now it's a very bad connection. I've connected an antenna, but at least from a DC standpoint, now the output is referenced to the chassis. So now we're not getting the bouncing anymore, but we are still getting significant noise and ringing noise at the transitions. That's where those are the switching transients from just the action of the switching power converter. Recall this thing is operating at about 400 kilohertz, so about a 2.5 microsecond period. It's at 1 microsecond per division, so that's what we're dealing with. It's about a 2.5 microsecond period. That's what we're seeing here. So all that's as expected. It's a deliberately, it's not filtered or anything like that. So I kind of expect it to be graphic. So I need to put an offset on our output as well. So let's do that. Expand that a little bit. Okay, it's still yelling at me that channel 4 is clipping, so. Okay. So the yellow trace is our primary power input. The red trace is our plus 15 out with respect to chassis, with respect to the ground plane. And the green trace is our common mode current going into the end. That's our main monitor point for our injected signal level. All right, so I'm going to do a quick frequency sweep. Like when we do this for real, you're going to do a sweep from 10 kilohertz to 200 megahertz. You know, you do it per the mill standard, you would use their step sizes. For this streamlined version, I use 2% frequency steps. Generally, we would dwell at each frequency for 1 second. For what we're dealing with here, just looking at the output of a power converter, we don't need that. Also, it'll be much quicker to, let me see, I've set it for, dwell is, well, it's 100 milliseconds. So it'll be 10 times faster. Going from 10 kilohertz to 200 megahertz with 1 second dwell time, 2% step size, it takes about 8.5 minutes. So it'll take about a tenth of that amount of time. It'll take a little less than a minute. So that's a little more palatable for a demonstration. And so we'll go ahead and set this up for a continuous sweep. I may need to adjust signal levels to accentuate things, but let's let it roll. We'll set it for auto. So it should start over again. When it gets back to, when it hits the end, it'll wrap around and start over again at 10 kilohertz. So there's not much yet. At low frequencies, you know, there's not much current getting through. I'm going to expand that a little bit. When I did this yesterday, it was up at a couple megahertz, I think was when you actually started seeing anything. Okay. Oh, you know what? What didn't I do? I didn't turn RF on. There we go. Let's start over. Let's turn RF on and we'll start the sweep over again. All right. And
But he was not sleeping.
no, it was sweeping. It just the RF wasn't on. All right, you actually are seeing you're starting to see pretty good wobble on the input now, but not much is getting through yet. We're at 500 kilohertz, so a little above a megahertz. Okay, now you're starting to see significant amount of current getting through on our monitor probe. Not a lot's getting through on the output. Now it's starting to come up. Now on the output, we're getting, that's about 7-8 megahertz. That's about what I was seeing. Okay, and then once you get up to, it's about 50 megahertz now. Current's coming up a little bit more, but then not much is getting through, but okay, it's wrapped around now. But at the higher frequencies, it kind of settles down. But so let me do this. I'm gonna slow the dwell time down. I'll go to 200 milliseconds. It'll be a little bit easier to see what's happening. Just slowing it down by a factor of 2. Okay, so it started over again. All right, starting over again at 10 kilohertz. So now it's about 200 milliseconds per frequency step. So you can see that there's a bit of wobble on the yellow trace. That's our primary power input. But not much is getting through on the secondary or on our current probe yet. Now it's just unfortunate that we've got these nasty switching transients here that are minimizing our ability to see, you know, the ripple current that we're deliberately injecting. But once it comes up, you can definitely see it. So at the low frequencies, the impedance is high enough that you're not getting much current. Now we're at about 600 kilohertz. All right, you're definitely starting to see some of the current ripple getting in on our current probe. And it's clearly the same frequency, right? That is our injected frequency. No mistaking it. but the output is actually still holding pretty stable. Now there's some ripple coming up on the output. And now that the current is definitely noticeable as well. So you're getting to a point where the input impedance is low enough that a significant amount of current is coupling through. So this is just kind of a quick, crude qualitative demonstration of how you would do this injection after the pre-calibration. Pre-calibration is crucial. That's for characterizing what you're injecting. Right? You're injecting a potential, and then the current is going to be determined by the impedance of the loop, which you don't have any control over. Really, it's just whatever the impedance of the loop is formed by the cable under test in the ground plane. But you establish what that, at least that open circuit potential is during the pre-calibration step, and then you're monitoring the current basically to verify that you're actually, injecting, that you are indeed injecting a signal. There's kind of no doubt about it from what you're seeing here, but that's that voltage probe that you might not normally have access to. In this particular case, I already had that little test point set up, so I'm using it. But when you're injecting with a real system, you're going to be looking for establishing your pre-calibrated power level or signal generator level. But then you're also, if you hit 6 dB above the pre-calibrated current limit on the high frequency plateau, if you get 6 dB above that level, then you will stop. You will dwell for the preset amount of time, 1 second or 3 seconds or whatever it is you've set, and then go to the next frequency. That's how you do with a full up test system, and we'll set up a different session for seeing how you would do that with a proper setup, for the record. But we have used a version of this very setup to do actual runs for the record, and we can do it, much more quickly. Like I said, we can do a single cable in about 8.5 minutes, where a full up scan with the leveling, the leveling at each frequency is what adds a fair amount of time to it. I believe each cable can take about an hour. So doing a CS114 scan on each individual cable just for common mode can take about an hour. So if you got a lot of cables, that can add up. You got a couple dozen cables, that could be a couple days just to do CS114. But at least for an early diagnostic, using this simplified setup, you can do each cable in under 10 minutes. That's a pretty valuable tool to have in your belt. And you would do this, you would monitor things in the frequency domain, by the way. This just gives you a cruder idea of what things will look like just in the time domain, just on the scope. But you can definitely see that the current is getting through here. And then it's also getting through on the voltage output. I don't actually recall, but I think when I looked differentially across the output, it didn't look too bad by and large. I'm going to go ahead and move the reference of the output to look across the output in a true differential manner. You see it looks a little better. You're seeing some of the switching transients there. I'm going to blow up the scale a little bit. And okay, the sweep just wrapped around. It's back at about 17 kilohertz now. And so when we see our current pickup, let's see what happens to our output voltage. The output is the red trace in the middle. At about 100 kilohertz. I think the current is starting to pick up. We're at about 500 kilohertz. So yeah, there we go. Current's picking up around a megahertz. So the current's getting to be pretty significant, but the differential potential across the output is not too bad. Now you do this in the frequency domain to be a bit more quantitative about it, but and again, there's some picking up now. Because that's really your ultimate figure of merit is what is the differential potential across, coming out of your power converter. And you're doing common mode injection here, but how much of that common mode is converting into a differential mode signal that's getting onto your output potential? If you got that much common mode, it's not good either, but then, that comes down to grounding and filtering and stuff like that. But that gets into design, which is the subject for another discussion. But that is basically what I have to show you. Does anybody have any questions? Are you still there?
Yes.
Okay, well, if there are no questions, thank you very much for participating again today, and we'll get the recording out as soon as it's available, or as soon as I can make it available. And I actually have an 11 o'clock meeting that I may be able to make. So thank you all. Have a great day.
Thank you.
John,
Thanks.
Thank you.
thank you so much.
Thank you.
Yep, you're welcome. Have a great day.
Thank you.